Good day, viewers all over the world. You are welcome to Toydale online class. Today we want to look at the concept of line integrals. Line integrals. Line integrals. So as we have it on the board, line integrals. Line integrals. As we have it on the board, that let's see be a curve in an xy plane. This is an xy plane. Here is y and this is x. So in an xy plane, which connects points A and B. This is point A, this is point A, and this is point B. So let's see be a curve in an xy plane which connects points A and B. Point A has A1, B1. Then point B has A2, B2. Those are the coordinates of the 2 points. So we also said that we should let P and Q be single valued functions defined at all points of C. That is, P and Q are single valued function defined at all points of C. Okay, and that's what we try to sketch out in this other side. Then we now say that the line integral along C, is denoted as integral along C P dx plus Q dy, or integral. This line integral, of course, using this line integral can be split using Frobenius theorem. So we can split it as, this the coordinate of A is A1 B1. So from A1 B1 to coordinate of B, which is A2 B2. We can also have the integral and then we have this value. So where C is the curve y is equal to f of x along A and B. So this C is the curve. So if we bring C here, we want to talk about P and Q now. P and Q, which are single value function. So at this point C, we can draw a straight line. Then we generate this perpendicular distance. So from this point C to this point, this is the vertical. This is the change in x. That is, this is x value. This will the x represents change in x. Then along the horizontal is y. So this represents change in y. So Q has to do with it has to do with change in y. YP has to do with change in x. So whenever we talk about line integrals, we should note that C is a curve along xy. Though this is actually different from a straight line. No, when we have a straight line, we have equations of a straight line depending on the nature of that straight line. If you are given a straight line, the equation of a straight line is y is equal to mx plus c. But if that straight line passes through the center, c is going to be 0. It will be y equal to mx. But in this case now we are talking about line integrals. That is, the line in this case is not really a straight line. It's curve-like. It's like a curve. Okay. So how do we now find the line integral of this type of problem? By formula, it's given as this. It's given as integral P, which is the change along the x-axis, and Q, which is the change that we have, change in the value of y, but they are single value functions. So we should take note that they are single value functions. So the formula to find the line integral, is what we have there. So to find the line integral, the formula to find the line integral when we have xy plane is integral C P dx plus Q dy. That's the formula to find the line integral when we have xy plane. Then what if the line integral along a curve is 3-dimensional space? That is, if you know this, what we have there, the diagram we have here is just two-dimensional, y and x. What we have, x, y, z, three-dimensional. The line integral will be given as integral, the point C into brackets. When we have three-dimensional, no, this two-dimensional. When we have three-dimensional, what will be the line integral? The line integral by formula will be given as, let's say, a1 dx plus, we can say, a2 dy plus a3 dz. So this represents the line integral. So where a1, a2, and a3 are functions of x, y, and z. So in this case now, a1 is a function of x, a2 will be function of y, a3 will be function of z. So when we want to find the line integral of three-dimensional space, we go ahead and apply this. But when we have two-dimensional space, that is xy plane, p is a function of x, yq is a function of y. So depending on what we are given and what we are required to find. So this is how to find the line integral. Line integral when it is two-dimensional, xy plane. Then when it is three-dimensional, we go ahead and find this. Okay, so let's quickly look at some of the properties of line integrals. We're going to talk about the basic properties of line integrals. We are going to talk about three properties of line integrals. So line integrals have properties which are analogous to those of ordinary integrals. Properties. Let's quickly look at the properties. Properties of line integral. So we want to quickly look at properties of line integral. So let's quickly look at properties of line integral. The first one is that, the first property is that when we have integral p dx plus q dy, this is the same thing as it is linear, that is, it can be splitted. We say integral p dx, we can split it, plus integral q dy. That's the first property of line integral. That is, under line integral, we can actually split it. Then the second one is that, the second property is that if you have integral, like what we have there, let's say a1 b1 to a2 b2. These are coordinates. This is coordinate of a and that of b. So if we have this now, p dx, p is a function of x and q is a function of y. So what can we say about this? This is the same thing as minus integral. When we now interchange, we bring this lower to upper, upper back to lower. It's going to attract a negative sign. These are some of the properties of normal integration. For those of us that are familiar with properties of normal integration, then we are going to have p dx plus q dy. So this is what we are going to have. This is the second property. This is the second property. In this second property, when we interchange upper, this upper band back to lower band and vice versa, it's going to attract a negative sign. Then the third property, that is the third property of this line integral now is when we have integral a1 b1 a2 b2. If we have this line integral a1 b1 p dx plus q dy, this can be splitted. We can start to split this to integral a1 b1, then a3 b3 p dx plus q dy, okay, then plus integral a3 b3 back to a2 b2 p dx plus q dy. So we can actually have something of this nature. So we can have something of this nature. That is, we can decide to split this. We can decide to split this. When we are from a1 b1 to a2 b2, we can break it down to a1 b1 to a3 b3, then back to a3 b3 to a2 b2. That is, in that case, we are a3 b3 is another point. That is, this point here. This point here is another point. We are a3 b3 is another point. Is another point. Is another point on C. So instead of having just a1 You know, A1B1 from from what we stated earlier is the coordinate of A, capital A. Then A2B2 is the coordinate of B. So if you now have another point, say G, which is A3B3. So we can actually move from A1B1 up to A2B2 directly, or we move from A1B1 to A3B3. Then now we move from A3B3 back to A2B2. So the property is just telling us that if we have another point along that C, along that point, along C, we can actually split it. It can be splitted as we have it on the board. So let's take notes of all these properties. These properties are actually, they are very important when it comes to line integral. Where C is the curve. So I want us to take note of this. So in our next video, we are going to give example. In our next video, we are going to give example on line integral. So let's go through this note and see that we understand. And if you have any question, you can actually comment. Just write it at the comment section. I promise to attend to the question. Thank you.